Okay, I guess we'll start. So, hello, thank you for coming. I'm pleased to introduce my friend and collaborator, Paul Eigenthaler. He's originally from Vienna, so he did his undergrad and graduate studies at University of Vienna with Bodo Ziegler.
Oh, Bernhard Zeilinger, and then I was working with Bodo Ziegler, yes.
Okay. And then he started his postdoc at Universidad Católica in Chile, where we worked in this whole group together on everything dwarf galaxies. So he's still there now doing your second postdoc, I believe. And so he's going to talk about some work that we did in the Fornax Galaxy Cluster. So take it away, Paul.
Thanks, Matt, for the introduction. Thanks a lot for giving me the opportunity to talk here at Gemini. It's a pleasure, and it's always very nice to come to Hawaii. I envy you all because you have this very nice workplace here. Yeah, anyway, so what we do in Santiago at the Católica University, in the group of Thomas Pucia, we work on the Fornax Galaxy Cluster. And so there are many different people working on this, right? It's the next generation Fornax Cluster survey. So some people work on globular clusters, ultra-compact dwarfs. So I personally work on dwarf galaxies. And so the head of our group is Thomas Pucia, then Matt, of course, we work very close together, then Jasna, but then she's working on nuclei, and also many other famous people, for instance, Laura Ferrese and others. Okay, but let me get right into it. So why do we do this? Why do we do this new survey in Fornax? So the main idea is really to update old and existing catalogs in Fornax, right? So if we look at dwarf galaxies, the only catalog that was there was from Ferguson in 1989. I mean, there have been other catalogs, but none covering the whole cluster. And the idea is really, because in the local universe, people have found very ultra-faint dwarfs and ultra-diffuse dwarf galaxies nowadays. So the idea is really, can we detect them also in the Fornax cluster, right? And for instance, to solve the missing satellite problem. Because we know from simulations that there should be much more dwarf galaxies than we observe. And then we want to estimate the faint end slope of the galaxy luminosity function, of course, and measure structural parameters for all these dwarfs in the Fornax cluster, study their distribution within the cluster, measure stellar populations, and in the future also measure star formation rates and so on. So to do this, we need a very big detector, right? Because we have to cover a large area of the sky. And what you see here, so this is the next generation Fornax cluster survey. And one pointing here, right? This is one pointing of the DECAM instrument. And this covers 62 CCDs. And with this coverage, we can really map the whole Fornax cluster. So you see, with the central tile here, we can get around 1/4 of the viral radius in Fornax, and then this inner ring here, we can get out to half a viral radius approximately. And so the Fornax cluster, why do we study it, right? So because it's the most nearby southern galaxy over density. In the northern hemisphere, we have the Vigo cluster. In the southern hemisphere, we have Fornax. It's around 20 megaparsecs away, so it's very nearby. And this is why it's a goldmine for studying galaxy evolution and dwarf galaxies. And you see this is a huge area. We cover 30 square degrees. This corresponds to around 1.5 square megaparsec. But all these numbers don't tell us a lot, so it's much better to show, to visualize this more properly. We are here at Gemini, so let's compare this with something you're much more familiar with, GMOS. So now that's the GMOS field of view. So you can imagine what we're talking about here. It's really a huge area. We have so much data, and it's a lot to analyze. Okay, so now we have a look at the central tile. This is just the very central tile, 1/4 viral radius. And you already can see all the famous big galaxies, and still not a lot else. But if we zoom in, right, you can already see there are some faint structures here. And if we zoom in a little more, you can already see, so these are all the faint dwarf galaxies we detect. So for instance, this one has been detected already many years ago, but now we can see much fainter ones like this, even these, so they're extremely diffuse. Yeah, again, and so this was only the central tile.
Can I ask how you confirm that it's actually in the cluster and not something like
so all of this is done photometrically.
Okay.
So technically, we don't confirm the membership. Yeah, we would need spectra for all these dwarfs, and it's very time-consuming and challenging. But we have, from photometry, we have very good ideas that they are cluster members, right? But of course, you're absolutely right, we cannot be 100% sure. Just so how we did this, we detected all the dwarfs by eye, because if we do this automatically, right, with Sextractor, it's very tricky because they are so faint that Sextractor doesn't find them. And actually, the referee for the paper made a comment and said, so why you don't do that automatically with Sextractor? And then I tried it, and it really you really see that at a certain surface brightness, it breaks down, right? It doesn't detect them anymore. And also these dwarfs are contaminated, of course, by stars and so on, so it's impossible. So what we did is by eye detection, and to really quantify the selection, our selection function or the human bias, we introduced quality flags. So what you see here, every ring is a dwarf detection, and every color represents a different person, right? And so we did this 5 people independently. So Matt was one of the guys that detected dwarfs. And so what you see here, right? So if there are more circles, different colors on one detection, this means, of course, more people independently detected dwarf. And for instance, so then we came up with these different quality flags, right? So here it means, so we were 5 people, all 5 people detected a dwarf. And then as we go on, if we subtract these, then 4 people, right? So it's, of course, you have to always cross-match every catalog with every other catalog. So there are many combinations. And then in the end, of course, there are those candidates that only one person detected. So we didn't take them seriously, right? Because it shows you, right, that there is an individual human bias, because some people might detect something, I don't know. And it's interesting, there are some people who are very, very eager to detect.
Well, whoever was red, I think, started drinking the wine, scanning through the top. They finished drinking by the bottom.
Yeah, that's interesting to see, you know, because you clearly see that different people have a different bias. And then we came up with these quality flags, right? So what you see here on the bottom, quality flags. So flag A means all 5 people independently detected the dwarf, and flag E would be only one person detected the dwarf. And you see a clear bimodal distribution. So, of course, the number goes up for only for where only one person detected the galaxy, right? Because it multiplies. If you divide this number here by the number of people who detected it, it's exactly continuation of this function. And what's much more interesting is that as we go towards higher quality flags, we have a monotone increase, right? So there's a clear trend towards unanimous detection. And then I also checked, is there a correlation with galaxy parameters, right? Like the integrated magnitude, effective radius, or surface brightness. So we see that there's not a clear correlation with the surface brightness, and integrated magnitude is also more or less, there's not a clear trend, but effective radius strongly affects the detection, right? So if you have a larger galaxy, it's much more probable that all 5 people detected it. But if it's smaller, it's much more likely that someone detected it, someone didn't. And then we came up with the final catalog. So yeah, in the end, we decided that out of the 5 people, right, at least 3 had to detect the dwarf. So we made the cut here. And we considered all these detections, and all the others we didn't consider detections. And what you see here now is what we found in the central tile. So we found 258 dwarf candidates. And this is why we speak of candidates, right? Because they are not really, we cannot confirm them. Yeah, and out of those, 121 have previously been uncatalogued. And what's also interesting, we see that around 30% of these are nucleated, so they show a nucleus. So here you can always see the nucleus, the nuclei indicated by the black dots. So the orange galaxies are the bright ones, the bright cluster members, and the red ones are all the dwarfs. And there are many. And we published this year. Yeah, there are many galaxies, but there are even more. So this we also published this year, and now we're covering already the whole central ring, right? This is out to half a Virgo radius. And here we have 643 dwarf candidates. And we find a similar nucleation fraction around 30%. And the interesting thing is that now we have a very homogeneous sample, and we can study all the galaxy parameters within this sample, right? How the dwarfs distributed, are there planes, is there a color, is there any color relation within the location, with the location in the cluster, right? What we did is really, we looked at the spatial distribution of the galaxy light, right? We wanted to analyze the surface brightness profiles. And what you can see here is on the left, there are 4 typical non-nucleated dwarf galaxies, and on the right, 4 nucleated dwarf galaxies. And they're always decreasing in surface brightness. And then we fit Cerseic models to these light profiles. And so for the brighter ones, it's very clear that we can fit them. But also, it's very nice to see that also for the fainter ones, we really can fit them, and it works very well. So since the dwarfs are a very simple objects, we can all fit them with one component. And as you can see in the residuals, it works very well. So also, if you have a lot of contamination here from background galaxies, we can very nicely separate these. And trust me, there are much, much worse examples. These are pretty ones. And it always works. It just takes a lot of tweaking. So in the beginning, I fit all the dwarfs automatically, but then you always have to iterate on it. You have to really tweak, and then it works quite well. Yeah, this just shows you the surface brightness to give you an idea, right? So we really go down to 28, 27, 28-ish in surface brightness, magnitudes per square arc second. So we reach already regions where the intracluster light is present. And yeah, based on this analysis, of course, then we can study the structural parameters. And we did this in 3 passbands, in I, G, and U. And what's also interesting is that, of course, U band is the tough band, right? Because you need so much integration time, and the observations are much shallower. But even there, so we don't get proper morphologies for all the U band galaxies because they're just so shallow. But still, we can measure the properties for many galaxies. What's also interesting, I just show this because it shows you how one has to really do this properly. For instance, if we have a nucleated galaxy, you have to do we did an iterative fitting approach, right? So first, so that's the galaxy, then we fit it, and obviously what you see is it overfits the galaxy model, right? Because it tries to fit the nucleus. And then it makes the profile too steep, and then in the residuals you get this, you see that it's wrong, right? So what I did then is, based on this first fit, I generated a mask, and then fed the mask back into the fitting procedure, and so on and so on. And then you see, as if you do this process for a few steps, it gets much better, and then you can separate the nucleus and the spheroid very well. So the thing is also, in GalFit, you can fit the nucleus, you can fit multiple components. You can fit the nucleus and the galaxy spheroid independently, and we tried that. But it always turned out that it worked much better this way. Because also, if you add more components, of course, then you have more degrees of freedom, right? And this way it worked much better. And then we got all the structural parameters. So what you see here is a comparison between the passbands. So in the x-axis, always you see the I band, and in the lower panels you see the G band, and the upper panels the U band. So you see effective radii, ellipticity, position angle, they all agree very well. So this shows us simply that what we did is not completely wrong. And then we get all the distributions of our parameters, right? So you see certain indices are around 1, as we expect for dwarf galaxies. Effective radii are between or around 0.5 kiloparsec, right? Ellipticity, there is no trend really. So if you see this here, we see probably 2 peaks, but we check this if this are 2 different distributions, but we can confirm this, and position angles are very homogeneously distributed. And then what's interesting is, of course, since we have the color information, to look at the color magnitude diagrams. So all the red dots are the dwarfs we detected. And what we did is we compared this with other galaxies in the nearby universe. So for instance, the dark dots here are from the Next Generation Virgo Cluster survey. And then we also compared with the Illustrious and Eagle simulation, right, in blue and green. And yeah, we see that our galaxies really fall on these sequences, so they're not totally off, so it seems reasonable. And what's much more interesting is to compare, based on this color information, to compare the dwarfs with Brusel-Chalot models, right? So what you see here is the histograms, so the distribution of colors. And then I plot here the SSP models, Brusel-Chalot SSP models. So what they show you is for a certain age, they predict a certain color, right? And the different colors here in the lines are different metallicities. So essentially what you see is that, so this shows you essentially the age metallicity degeneracy, right? Because you can have a galaxy that is a galaxy with a high metallicity that has a certain age, but it has or it is comparatively young, but it can have a higher age with a lower metallicity, right? So this spread here shows you essentially the age metallicity degeneracy. And to break this degeneracy, we really need infrared data or, of course, spectroscopy, but that's very, very time consuming to get. So to understand these diagrams, what you essentially have to do is, right, you have to intersect here the distribution of the dwarfs with these lines, and then you see, okay, they are here, for instance, the age is 1 gigayear if you assume solar metallicity. But for instance, we know from the mass metallicity relation for dwarf galaxies that we expect for these dwarfs metallicity is much, much lower, right? So we can expect that they are older than 5 gigayears. Anyway, this is just based on the data we have. I mean, with optical data, it's very, very tricky to do this. And we need K-band data to break the degeneracy more. And yeah, let's see. We wrote many proposals to get follow-up spectroscopy, but you can imagine it's very, very, very time consuming. Now with all the structural parameters, of course, we want to look at scaling relations, right? And that's what we did. So all the red dots here are, again, our newly detected dwarfs. And the interesting thing is, so the yellow dots here are local group dwarf spheroidals. So now we really reach, at a distance of Fornax, we reach the regime of local group dwarf spheroidals. So previously, these very, very faint dwarfs have only been detected in the local group, and now we detect them already out in more distant clusters. So there are many different samples here. These are bright ellipticals, right? These are, for instance, nuclear star clusters and UCDs. These are globular clusters. What's very interesting, these are ultra diffuse galaxies, right? So for a given, so here on the x-axis you have stellar mass, and here on the y-axis you have effective radius. So for a given stellar mass or magnitude, right, ultra diffuse galaxies are larger, right? So this means their surface brightness or stellar mass density is lower. So all these diagonal lines here give you always lines of constant surface brightness or stellar mass density. And this is very interesting now, because if we look at, for instance, our dwarf sample, we see that the inclination of the dwarf sample is shallower than these isodensity lines. And for bright ellipticals, it's steeper. And this dichotomy has already been known for many years. So the first one who mentioned this was Cormandy in 1977. And now with our data, we have so many galaxies, right, that we can have a clear look at that. And so what you see here, we fitted 2 lines non-parametrically. So the brown line is connecting all the dwarf galaxies with the bright ellipticals. And the blue line connects the dwarfs with spiral galaxies, white spiral galaxies. To just get an idea how these systems are connected. And if we look at the brown line, right? So all early type galaxies, we see that the slope. So here we see in this panel, we see the slope, right? So here around 0.5, this would mean the slope along the isodensity lines. This would mean if the galaxy grows along the isodensity lines, it doesn't change its shape because it gets more massive, but also the effective radius increases this way that the density stays constant. And we see here that now for the brown line, the slope is below this isodensity line, right? This is what we see here, it's flatter. And then it goes completely flat. So this means the galaxies get larger or get more massive, but don't increase their radius. And this means if you put more mass into the galaxy, but it doesn't grow in size, it means it automatically gets denser. This is why it intersects here the isodensity lines. And then for the massive ellipticals, it's the opposite, right? They grow larger in size compared to the accumulation in mass. So this is, you see here, the line, the gradient is higher than the isodensity line. And to show you this much clearer in a nice diagram. So if you have, so let's start here. We have a galaxy, right? It has a certain effective radius. And then if the galaxy accumulates mass, along the isodensity lines, yeah, it gets bigger, more massive, but the effective surface brightness stays the same, right? Because you just blow it up. But if mass is assembled within the effective radius, you increase the effective surface brightness within the effective radius, and essentially the effective radius gets smaller than before, right? So what I mean, the effective radius gets larger compared to the initial galaxy, but not comparatively as large as it would grow along the isodensity lines. In the isometric growth, right, you add mass everywhere. This means the effective radius stays the same, but just the galaxy gets denser. And for the halo mass assembly, it's the other way around. The effective radius gets increased because more mass is added in the outskirts. So and this is essentially what we see in this diagram. So we claim that up to a certain mass around here, right, the galaxies assemble their mass more within the effective radius. Here we see an isometric mass assembly, and here it's more halo mass assembly. And this does not necessarily mean that this is a hierarchical scheme. It just shows you that's what we see, right? And the galaxy has to, so that's a snapshot what we see now. And the galaxy has to land on the sequence. And all I want to say is the following, like a galaxy here assembles the mass differently than a galaxy than here. If you compare the light profiles of those two galaxies here, it means that for a galaxy here, more mass is added within the effective radius than outside. And yeah, here you see another same plot, just with the mass density, the y-axis, and the stellar mass on the x-axis. Yeah, it's essentially the same. What you see one much nicer here is that the ultra-diffuse galaxies are really detached here. And yeah, to summarize, we have found many galaxies, 640 galaxies within half the virial radius. Around 30% show a nucleus. So we have also published other papers just focusing on the nuclei. The dwarf galaxies are very well presented by single component Cerseic profiles. It's also interesting to see because if we go to more massive dwarfs, we start to see more complex residuals. It shows you that there the galaxies have more complex formation scenarios, right? In the transition to the bright ellipticals. Yeah, we see a flattening of the red sequence, as has also already been seen in the Virgo cluster. Based on the SSP, post-Chalot SSP models, we see that the dwarfs are old and metal poor, but again, as I said, this is very tricky because we have to get more data, K-band data, to investigate this further. Yeah, we confirm many dwarf galaxy scaling relations. And yeah, we have this picture of the mass assembly. So based on the slope of the scaling relations, we conclude that the mass assembly works like that. And just to give you a little outlook, so we have lots of data. So we're working also on color maps, right? So you can see, so for every pixel we can compute a color. So you see here we have galaxies that are more star forming, that are bluer, but the majority, of course, is very homogeneous, old, as you've seen in the color magnitude diagram. Yeah, we have K-band data that is being analyzed. And what's also interesting, so we want to measure the galaxy luminosity function. And let me see if this works here. And so what you see is here just a histogram, right, of the number of the dwarf galaxies. We have to estimate the galaxy luminosity function. And as you can imagine, it's very tricky because we have to model our completeness, right? Where's our completeness? I just drew this because of course we have to know where to stop, right? Because, can I show this again? For instance, here we get incomplete, that's for sure, but for instance, the correct, oh no, don't know. See, yeah, so the correct slope will be somewhere around here, right? And now what we're doing is we have to model our completeness, really to know where we start to get incomplete, and then we can measure the faint end slope of the luminosity function. But you see, this is a log scale, and of course here there are many galaxies, right? So we have to really be sure. We have to generate mock catalogs to test our completeness, detect them, and so on. Yeah, that was a brief overview what we do. There are many other projects we're working on, but that's the main.